An electrical inspector cited a violation for no ground on a metal box. The contractor is confused because the ground wire wasn't connected to the metal box during the rough electrical phase. The contractor typically expects the ground wire to be connected to the box during the final installation phase. The inspector requested that the ground wire be connected during the rough phase. While there is no explicit code reference regarding connecting the ground wire during the rough phase, the inspector may have had safety concerns in mind. By connecting the ground wire to the box during the rough phase, it ensures that the metal box is grounded throughout the construction process. This is especially important if other metal components, such as drywall screws, come into contact with the box. It is important to communicate with the inspector to clarify their reasoning. If the inspector can provide a valid safety concern, it is advisable to comply with their request. However, if the contractor believes the request is unreasonable, the contractor can provide technical documentation or consult with an electrical engineer to support their position. Grounding is a critical safety measure in electrical systems. It provides a low impedance path for fault current to return to the source, which helps to trip a circuit breaker or fuse and to energize the circuit in the event of a fault. This protects people from electric shock and prevents damage to equipment. In general, all metal enclosures that contain electrical conductors or equipment must be grounded. This includes metal boxes, cabinets, conduits, and equipment frames. The grounding conductor must be sized appropriately for the circuit it protects, as specified in the National Electrical Code, or NEC. The NEC provides detailed requirements for grounding electrical systems in Article 250. This article covers topics such as grounding electrode systems, grounding conductors, equipment grounding, and bonding. It is important for electricians and contractors to be familiar with the requirements of Article 250 to ensure that electrical systems are properly grounded. The purpose of grounding metal enclosures is to provide a path for fault current to flow back to the source in the event of a fault. This helps to trip a circuit breaker or fuse and to energize the circuit, which protects people from electric shock and prevents damage to equipment. When a fault occurs, such as a wire coming into contact with a metal enclosure, the fault current will flow through the grounding conductor back to the source. This current will cause the circuit breaker or fuse to trip, which will de-energize the circuit and stop the flow of current. If the metal enclosure is not grounded, the fault current will not have a path to flow back to the source. This can cause the metal enclosure to become energized, which could create a shock hazard. In addition to providing a path for fault current, grounding metal enclosures also helps to reduce electrical noise and interference. This can improve the performance of sensitive electronic equipment. Electrical noise can be caused by a variety of sources such as lightning, radio transmissions, and electrical equipment. Grounding metal enclosures helps to shield the equipment from this noise. There are several different ways to ground metal enclosures. One common method is to use a grounding screw or lug to connect the grounding conductor to the enclosure. The grounding screw or lug must be properly sized for the grounding conductor being used. Another method is to use a grounding bushing to connect the grounding conductor to the enclosure. A grounding bushing is a special fitting that is designed to provide a secure connection between the grounding conductor and the enclosure. The NEC requires that all metal enclosures that contain electrical conductors or equipment be grounded. This includes metal boxes, cabinets, conduits, and equipment frames. The grounding conductor must be sized appropriately for the circuit it protects, as specified in the NEC. Article 250 of the NEC provides detailed requirements for grounding electrical systems. This article covers topics such as grounding electrode systems, grounding conductors, equipment grounding, and bonding. It is important for electricians and contractors to be familiar with the requirements of Article 250 to ensure that electrical systems are properly grounded. Grounding is a critical safety measure in electrical systems. It provides a low impedance path for fault current to return to the source, which helps to trip a circuit breaker or fuse and to energize the circuit in the event of a fault. This protects people from electric shock and prevents damage to equipment. The inspector's concern about grounding during the rough-in phase may stem from the potential for accidental contact between rounded metal boxes and other conductive materials during construction. For example, if a drywall screw pierces the metal box and contacts an energized conductor, the entire box could become energized, posing a shock hazard to anyone who touches it. By grounding the box during the rough-in phase, this risk is mitigated. While it is common practice to connect the ground wire during the final installation phase, some inspectors may prefer grounding during the rough-in phase as an extra safety precaution. There is no specific NEC code that mandates grounding metal boxes during the rough-in phase. However, the NEC does require that all metal enclosures be grounded, and it is up to the inspector to interpret how and when this requirement is met. Here is a breakdown of relevant NEC sections that support the requirement for grounding metal boxes. NEC 250.4 A1 states that electrical systems shall be grounded in a manner that will limit the voltage imposed by lightning, line surges, or unintentional contact with higher voltage lines, and that will stabilize the voltage to ground during normal operation. This section establishes the fundamental principle of grounding for safety. NEC 250.4 A5 states that equipment grounding shall be provided to create a low impedance ground fault current path and shall facilitate the operation of overcurrent devices. This section emphasizes the importance of a low impedance path for fault currents to ensure that circuit breakers or fuses trip quickly. NEC 250.8 specifies the methods for connecting grounding and bonding equipment. This section requires that connections be made using listed pressure connectors, terminal bars, exothermic welding, or other approved means. NEC 314.40 addresses the support of boxes. While it doesn't directly mention grounding, it's relevant because boxes must be securely mounted to facilitate proper grounding. NEC 406.4 D requires receptacles to be grounded. This is relevant because the metal box often serves as the grounding means for the receptacle. Here are some best practices for grounding metal boxes. Firstly, always use listed grounding connectors or lugs that are specifically designed for the type of metal box and grounding conductor being used. Secondly, ensure that the grounding conductor is properly sized according to NEC Table 250.122, based on the rating of the circuit. Thirdly, make sure that the grounding conductor is securely connected to the metal box and to the grounding system. Fourthly, when using metal conduit, ensure that the conduit is properly bonded to the metal box to maintain a continuous ground path. Fifthly, consider using self-grounding receptacles, which make a direct connection to the metal box when installed. Self-grounding receptacles are a good option because they provide a reliable ground connection without the need for a separate grounding jumper wire. To resolve the issue with the inspector, firstly, calmly and respectfully discuss the inspector's concerns and reasoning. Secondly, review the relevant NEC sections with the inspector to understand their interpretation of the code. Thirdly, if possible, provide documentation or evidence to support your position. Fourthly, if necessary, consult with a qualified electrical engineer or another authority to obtain a second opinion. Fifthly, if the inspector's concerns are valid, comply with their request to ensure safety and code compliance. Remember that electrical inspections are intended to ensure the safety of electrical systems and to protect people from electrical hazards. It is important to work with inspectors to resolve any issues and to ensure that electrical work is done in a safe and code-compliant manner. Here are some additional points to consider. Firstly, the inspector may be concerned about the potential for the metal box to become energized if it is not grounded during the rough-in phase. This could happen if a wire comes loose and contacts the metal box, or if a nail or screw pierces the box and contacts a live wire. Secondly, the inspector may be following a local code or ordinance that requires grounding during the rough-in phase. It is important to check with the local building department to determine if there are any local requirements that differ from the NEC. Thirdly, even if there is no specific code requirement, it is always a good practice to ground metal boxes during the rough-in phase as an extra safety precaution. This will help to protect workers from electrical shock and to prevent damage to equipment. In some cases, the inspector may be willing to compromise and allow the grounding to be completed during the final installation phase, as long as the boxes are properly supported and the wiring is protected. However, it is important to get the inspector's approval before proceeding with this approach. Here's more in-depth information about electrical safety. Electrical safety is a critical aspect of any construction or electrical work. Understanding the risks and implementing proper safety measures can prevent accidents, injuries, and even fatalities. Here are some key areas to focus on. Firstly, always de-energize circuits before working on them. Use a voltage tester to verify that the circuit is de-energized before touching any wires or components. Secondly, use appropriate personal protective equipment or PPE, such as insulated gloves, safety glasses, and insulated tools. Thirdly, be aware of your surroundings and potential hazards, such as overhead power lines, wet conditions, and confined spaces. Fourthly, follow lockout/tagout procedures to ensure that circuits are not accidentally re-energized while you are working on them. Lockout/tagout involves disconnecting the power source, applying a lock to the disconnect switch, and attaching a tag that identifies the person who is working on the circuit. Fifthly, never work on electrical equipment while standing in water or on a wet surface. Water is a conductor of electricity, and it can increase the risk of electric shock. Sixthly, use ground fault circuit interrupters, or GFCIs, in wet locations such as bathrooms, kitchens, and outdoor areas. GFCIs are designed to detect ground faults and to quickly de-energize the circuit, which can prevent electric shock. Seventhly, inspect electrical cords and equipment regularly for damage. Replace any cords or equipment that are damaged or worn. Eighthly, never overload electrical circuits. Overloading a circuit can cause the wires to overheat and can lead to a fire. Ninthly, use the correct size and type of wire for the circuit. Using the wrong size or type of wire can cause the circuit to overheat and can lead to a fire. Tenthly, follow all applicable electrical codes and regulations. Electrical codes are designed to ensure the safety of electrical systems and to protect people from electrical hazards. Now for a discussion on electrical panels and circuit breakers. Electrical panels and circuit breakers are essential components of any electrical system. They provide a central location for distributing electricity throughout a building, and they protect circuits from overloads and short circuits. Here are some key things to know. Firstly, electrical panels are typically located in a basement, garage, or other readily accessible area. Secondly, circuit breakers are designed to trip when the current in the circuit exceeds the breaker's rating. This protects the wiring and equipment from damage. Thirdly, always label circuit breakers clearly to indicate which circuits they control. This will make it easier to identify and troubleshoot problems. Fourthly, never replace a circuit breaker with a breaker of a higher rating. This can overload the circuit and can lead to a fire. Fifthly, if a circuit breaker trips frequently, it may indicate a problem with the circuit. Have a qualified electrician inspect the circuit to determine the cause of the problem. Sixthly, keep electrical panels clean and free from obstructions. This will ensure that the breakers can operate properly and that the panel does not overheat. Seventhly, never tamper with or bypass circuit breakers. This can create a dangerous situation and can lead to a fire or electric shock. Let's talk about the different types of grounding. Grounding electrode systems are an essential part of any electrical system. They provide a connection to the earth, which helps to stabilize the voltage and to provide a path for fault current to flow back to the source. Here are some key types. Firstly, the most common type of grounding electrode is a ground rod. A ground rod is a metal rod that is driven into the earth. Secondly, another type of grounding electrode is a ground plate. A ground plate is a metal plate that is buried in the earth. Thirdly, a concrete encased electrode, also known as a UFA ground, is a grounding electrode that is encased in concrete. Fourthly, a metal water pipe can also be used as a grounding electrode, provided that it is in direct contact with the earth for at least 10 feet. Fifthly, the NEC requires that all grounding electrodes be bonded together to form a grounding electrode system. This ensures that all parts of the electrical system are at the same potential. Electrical bonding is the process of connecting together all metal parts of an electrical system to create a low impedance path for fault current to flow back to the source. This helps to trip a circuit breaker or fuse and to energize the circuit in the event of a fault. Here are some key points about electrical bonding. Firstly, bonding is required for all metal enclosures, conduits, and equipment frames. Secondly, bonding conductors must be sized appropriately for the circuit they protect, as specified in the NEC. Thirdly, bonding connections must be made using listed pressure connectors, terminal bars, or other approved means. Fourthly, bonding is particularly important in areas where there is a risk of corrosion or moisture, such as bathrooms, kitchens, and outdoor areas. Fifthly, proper bonding can help to reduce electrical noise and interference, which can improve the performance of sensitive electronic equipment. It's worth noting that while the inspector's request might seem unusual, open communication and a willingness to understand their perspective are key to resolving the situation. Consulting with a senior electrician or electrical engineer can also provide valuable insights and help navigate complex code interpretations. Ultimately, ensuring the safety of the electrical installation is paramount, and finding a solution that satisfies both the inspector and the contractor is the goal. Remember to document all communications and agreements in writing to avoid future misunderstandings. Keeping detailed records of inspections, code interpretations, and any deviations from standard practices can be helpful in resolving disputes and demonstrating compliance.